please feel free to have tea, coffee, snacks, bhaji, vada pav, anything you want while solving the problem. It is not a it is not an issue at all. Okay. Okay. So now recording has started. Okay. Now, so Ram, tell me what do you think? Whether you got the answer, you don't have the answer. It doesn't matter whether your answer is right, wrong. Doesn't matter. There is no unique way of doing it. There are multiple ways of doing this.
Sir, I calculated this ratio humidity of both input and output.
Okay. So
Then
let's talk about input first. How did you calculate the humidity of the input?
first from dew point, I calculated partial pressure.
So dew point, you calculated partial pressure or vapor pressure?
Vapor pressure at 30 degrees
So vapor
Celsius,
pressure at 30 degrees centigrade you calculated. How much? What is the value?
31.65 mm mercury.
31.6.
65
Okay, it's 31.65 mmHg. Since the dew
mmHg.
point is 30 degrees centigrade, therefore partial pressure, yes, mmHg, therefore partial pressure of water vapor in the ambient air must also be equal to the dew point, that is 30 dew point vapor pressure at the dew point. So that must be also 31.65 mmHg. Okay, so now how did you calculate the humidity?
Then we know partial pressure of water vapor. Also, we know total pressure. So from the formula kg of from the formula we get partial pressure upon
Which,
total pressure
which,
minus
yeah, so 760 minus 31.65. This will give you moles of water vapor per mole of dry air, multiply by 18 divided by 28.84. That will give you kgs of water vapor. So what is the value?
0.0277
0227.
7
227.
0.027
027. So this is kgs of water vapor per kg of
per
dry
kg
air.
dry.
Okay. Now outlet, how did you do?
uh, Sir, I calculated vapor pressure at 80
Now,
degrees Celsius,
okay, so you calculated vapor pressure at 80 degrees centigrade. What is the value?
355.31.
355.31 mmHg. Now,
uh, since we know percent relative humidity from the
okay,
formula, I calculated partial pressure of water vapor.
correct. So that is 5%. So 0.05 multiplied by 355.31. Okay. So what is the value?
17.76.
mmHg. All right. So now
uh,
humidity,
yes.
17.76 divided by 760 minus 17.76 multiplied by 18 divided by 28.84. What is the
0
value?
point 0.0152.
0152 kgs of water vapor per kg of dry air. Okay, now what do you think?
Now, sir, since initial temperature is 35 degrees Celsius and final temperature is 80 degrees Celsius, so
Hmm,
whatever kg of water vapor were in the input should be
hmm.
equal to the water vapor in the output.
No, this is what is input and this is what is required, right? So I have to do something in between to make sure that I get this required humidity. This is my 0.0152 is my target. I can't say I won't give 0.0152, I will give something else, because the dryer performance will be dependent. If let's say this hot air is going to dryer, then the dryer performance will depend on the humidity, isn't it? We saw
Yes, sir.
we saw in the previous problem, the dryer problem, right? If I have some different humidity of the incoming air, it will not dry that much amount of milk into milk powder, right?
Yes, sir.
So now tell me, what do you think? What can be done?
Should we supply more dryer?
Now, where are we going to get dry air from? Who's going to give you dry air? Yeah, 1 second, Ria. Where are we going to get dry air from, Ram?
Don't know, sir.
One option is we go to Rajasthan, put some dry air in a tanker,
Mm,
or go to some desert in Egypt and get some dry air in a ship and then add. Is that a good idea? Bad idea?
bad idea.
Bad idea. So what else can we do? Look at the previous problem. Look at problem number one. What these problems that we did. Before that, we did some problems. We were trying to compress to liquefy some water, or we were cooling to liquefy some water. We wanted to condense out 80% of the water. Look at this problem. Are you able to see the screen?
Yes, sir.
Do you remember this problem?
Yes.
So now tell me, what do you think? What can be done? So you are right. If I just take this air, if I just heat to 80 degrees centigrade, then obviously kgs of water vapor per kg of dry air will be 0.027. But that's not what we want. We want 0.0152. That means I have to take out water vapor from the air, isn't it?
Yes, sir.
So how do you take out water vapor from the air?
Cooling.
Cooling,
So by condensing.
right? So if I,
Isobaric cooling.
yes, right. So if I do isobaric cooling, I will have to cool to such a temperature. That's what we would have to find out, so that the humidity becomes 0.0152. And then now if I heat to 80 degrees centigrade, then that humidity will remain the same in the heating process, because we are not adding any water, we are not condensing any water. Do you agree? So I'll have to cool below the dew point so that the water condenses out. Do you agree?
Yes, sir.
I will have to condense out sufficient amount of water so that the humidity of the air outgoing from the condenser or cooler, whatever way whatever way you want to call it, so isobaric condensation of water, so that the remaining air will have humidity of 0.0152. And then if I heat that air to 80 degrees centigrade, then I will have humidity equal to 0.0152. Do you agree with that?
Yes, sir.
Okay, so now this air that goes out of this cooler or condenser, what can we say about this air? What can we say about the relative humidity of this air? Ram, what can we say about the humidity of this air, relative humidity of this air? Will it be saturated with water vapor?
Which one, sir?
This air that goes out of the condenser. Are you able to see the screen?
Yes, yes, yes.
Uh, so this air that goes out of the condenser, what can we say about this air?
100%.
You don't seem to be very confident. Are you telling or you're asking? You're,
No, sir, I am not sure.
why not? Have you have we not done this problem where we cooled
Yes, sir.
something? Don't you recall this problem that we discussed in the morning?
Yes, sir. Got it.
isn't it? Do you agree or do you disagree?
Yes, sir. Yes, sir. It should be 100%.
Correct. So this air that is coming out has to be 100% saturated because water is condensing out of this air. And we want the humidity of this air to be 0.0152, isn't it?
Yes, sir.
So now if I take this as the humidity, let's say total pressure here also is 760 because we are doing isobaric cooling. So now in this air, partial pressure divided by 760 minus partial pressure of water vapor into 18 divided by 28.84 must be 0.0152. Do you agree with that?
Yes, sir.
So tell me now what is the partial pressure?
1 minute, sir.
Sir,
Yeah,
after the condenser, why is the relative humidity 100%?
look at this problem. Look at the problem that we did. This problem that we did. Are you able to see problem number 4 that we did today morning?
Yes, sir.
What did we say about the nitrogen going out of this condenser? Are you able to see or you're not able to see?
Yes, sir.
So do you
Yes, sir, it
agree
is
or
given.
do you, it is not given? Did I give this?
No, sir.
No, then or we look at this calculation last week that we did. We had ambient air, we wanted to condense out some water from it. Don't you agree?
Yes, sir.
Remaining air will have 100% RH. I did not give this because
Okay, okay.
water is water. Do you agree or do you disagree?
Yes, sir, I understand.
Rishabh,
Yes,
if
sir.
water is condensing out of this air, right?
Yes, sir.
So only that much water will condense and remaining air will have maximum possible water in the form of vapor,
Yes, sir. Yes.
isn't it?
Yes, sir.
So therefore that remaining air has to be 100% saturated. It has to have 100% relative humidity.
Okay, sir.
Do you agree or you disagree?
Yes, sir, I agree.
Okay, thank you.
So in this sum, could I have just dealt with moles,
Yeah, you could have dealt with moles, absolutely no issue.
taking a basis at the start and then
Sure, sure, you could have dealt with moles. Yeah,
thank
Ram,
you, sir.
what is the value of partial pressure?
Sir, 17.81.
17.81 mmHg. Now, because this air is having 100% relative humidity, it must have vapor pressure at a temperature. That vapor pressure must be 17.81 mmHg, isn't it?
Yes, sir.
Because we are condensing, we are cooling up to this temperature T so that the humidity reduces from 0.027 to 0.0152. Look at the previous problems that we did. We wanted to condense out from this air. We cooled and we condensed out some amount of water. Let's say 80% water we condensed in this problem we did last week. Here also we condensed out 80% of the water last week. If you don't recall, then please revise, go through the recording and see the concepts once again. This is not a TV serial that you can come and sit in front of the computer screen and just understand what is going on. You have to be up to date and you have to revise your previous lecture. So now using Antoine equation, Can we calculate this temperature T?
Yes, sir.
So tell me, what is the temperature?
Twenty point 34 degrees Celsius.
Okay, 20.3 degrees centigrade. So if I cool to 20.3 degrees centigrade, I will condense out enough liquid water so that the remaining humidity is 0.0152 kgs of water vapor per kg of dry air. Then I take this air at 20.3 degrees centigrade and I heat it up to 80 degrees centigrade. Then I will get my required air.
Or sir, we can pressurize it
Yeah, so
to.
I'm just coming to that. This is one option. Ram, do you agree? Are you comfortable?
Yes, sir.
Okay, can we go forward?
Yes.
Yes. So we talked about another way of condensing out water in the last week's lecture. Second option, one option was to cool, to condense out 80% of the water, the problem that we did last week, or maybe Tuesday, I don't recollect when. Or another thing that we did was to increase the pressure beyond the dew point pressure, isn't it? So either we cool below the dew point, so option one. So important point is to realize that humidity of the incoming air, either in terms of moles or in terms of kgs per kg, is more than the required humidity coming out of the heater. That is the important point to realize. And therefore, we need to condense out liquid water from the incoming air. Right? Then only that humidity of the remaining air will reduce. So what were the options for condensing out the liquid water? One was to cool below the dew point temperature. That is this option one. Okay. So if you cool to 20.3 degrees centigrade, enough liquid water will condense and we will be able to get the humidity, and then heat up to 80 degrees centigrade, we will get the required air. Right, that is one. What is the second option that we have seen in the last, like in last week, for condensing out water, is to increase the pressure. Right, let's talk about that. Arya, will you tell us, will you help us out through this option? Arya, will you help us out in this option?
Yes, sir.
Okay, so we will compress to higher pressure, let's say P,
Uh,
okay, and we might do this isothermally.
yes, sir. If we
Okay,
compress the
so the
gas
temperature, yes.
at 30
So
degrees Celsius.
so let's say we want to do it isothermally, so we will keep the temperature constant, 35 degrees centigrade.
Okay, sir. Uh, so we'll pressurize the gas so much so that the mole fraction that we want to achieve into the pressure that we will be applying will be equal to the vapor
Yes,
pressure at 35 degrees Celsius.
correct. So now I have this humidity of 0.0152. That's what we want, right? So what you're saying is, let's calculate mole fraction of water here. Is that what you're saying?
Yes, sir.
In the outgoing air? Okay, so mole fraction would be 17.76 divided by 760. How much is that?
0.023.
0.023. So now this air that is coming out after the compression, because we have condensed out water, or compressed out if you like, this air that is coming out at high pressure, let's call it as P, this air will have mole fraction equal to 0.023. Then we will do another step where we will reduce the pressure and increase temperature to 80 degrees centigrade, and then we will get our required air at 80 degrees centigrade having humidity of 0.0152 or percent RH of 5. Is that correct? Is that what you're saying, Arya?
Yes, sir.
Okay, so now if this air is at a pressure, let's say P, it has a mole fraction of 0.023. So partial pressure of water vapor in this air coming out after that compressor, after that compression process, this air will have partial pressure equal to 0.023 multiplied by P. That P is unknown, isn't it?
Yes, sir.
And because the air is coming out after the compression, from which liquid water has been condensed out or compressed out, whatever phrase you want to use, this air would have 100% relative humidity. That means if I find vapor pressure at 35 degrees centigrade, which is 31.65 mmHg.
No, sir, that is at 30 degrees centigrade.
Oh, sorry, 30 degrees centigrade. Right. So what is vapor pressure at 35 degrees centigrade?
42 mmHg.
42 mmHg. Thank you. Right. So now this air, because it is having 100% saturation, 0.023 into total pressure, that is our partial pressure. This must be equal to 42 mmHg, which is our vapor pressure. Therefore, P would be 42 divided by 0.023. How much is that?
1802.5.
Forget that 0.5, 1802 mmHg. So nearly 2.5 atmospheres or something like 2.7. So 1802 divided by 760. That would be 2.37. Right? Same as 1802 divided by 760.
2.37 bar.
2.37 atmosphere.
Yeah,
760
atmosphere.
atmosphere. Right? Small difference between bar and atmosphere, but let's be precise. So now if I compress this incoming air to a pressure of 2.37 atmospheres, then liquid water will condense out of it, because this pressure is more than the dew point pressure, and therefore the remaining air will have lesser mole fraction of water vapor, and then if I heat, I will get the required air. So these are the two options that we have. Do you agree? Do you disagree?
Yes, sir. The the
Yeah,
third would be using a combination of both by
yeah, correct. So I mean, I could compress partly, I could cool partly, and then I could reduce pressure and I could increase temperature, right? So in
also
any
al-
combination, yeah,
also we could use a desiccating agent.
fine. You could use a desiccating agent like concentrated H2SO4. Yes, that can be
Oh,
possible.
so H2SO4, I had a doubt that
Huh.
since it would be a liquid, it would also have some vapors. So wouldn't that, at least for the given process of milk solids, wouldn't that be hazardous? As in, it would interfere later on.
Oh yeah, yeah, yeah. For this milk process, definitely there is no option but to use hot air. We don't want to
So,
mix this milk and we don't want to mix this milk and sulfuric acid, right?
no,
So
but
what? No, I
in the
understand.
vapor there would be some a minuscule amount, not.
Yeah, 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 yeah. Correct, correct. So what you are saying is this hot air is going to milk dryer, correct? And now if I use H2SO4, say 98% H2SO4, and this going out would be, let's say, 93% or 95% H2SO4, this air that is going out will be saturated. Well, I should not say saturated. This outgoing air, yeah, okay, we can say saturated, because this outgoing air will have some partial pressure of H2SO4 as well. It will have partial pressure of water vapor. This air will contain water vapor because some of it has been condensed, has been absorbed by H2SO4. But because H2SO4 is liquid and air is coming in contact with that, it will be saturated with H2SO4 vapors. So we have to find out Antoine's constants for H2SO4. We have to find out, suppose we are doing this at 35 degrees centigrade. So we have to find out vapor pressure of H2SO4 at 35 degrees centigrade, and those many H2SO4, that much amount of H2SO4 will go in this air. You are absolutely right. And therefore, if we are using it for milk dryer, obviously it is a no, no, no. It is a small quantity, but you don't want people drinking H2SO4 unknowingly. You can tell them that, my milk is going to contain some amount of H2SO4. Would you like to buy and drink? They will say, get lost, right? But unknowingly, we should not allow people to drink H2SO4. So yes, absolutely right. So it is not a good idea to use H2SO4 as a desiccating agent. We might want to use silica gel. We might want to use some kind of, some things
Calcium
are
oxide.
called that, yeah, calcium oxide. Okay, but there are some better things which are called as zeolites. So zeolites are commonly used for dehydrating purposes. It absorbs water very strongly, and therefore we can get rid of the air, get rid of the water.
So, but it would be for liquid solutions, right? Zeolites, or even for gaseous solutions.
Zeolites are for gaseous solutions, gaseous components. Zeolites don't work that well with liquids for dehydrating purposes.
Okay, sir.
There are some things called as carbon molecular sieves, which sieve out water, but let's not worry about that. Yeah, so there are multiple options. The two options that we have seen so far is condensation by reduction of temperature below the dew point and then subsequently heating. Option 2, increase pressure, thereby condense out the water, then reduce pressure, then reduce the pressure, and then heat to the required temperature. So both these options are there. You can have any combination of these two as well. So you could have a cooling, you could have a compression, you could have a depressurization, and you could have a heating. Choice is yours. Any possible combination of these two are also possible. So any doubt so far? Anything we need to discuss? Can we go to the next part.
Sir,
Yeah.
in the desiccating agent part, if
Hmm.
is there any way that we can control the amount that gets removed?
Yes, we can use corresponding amount of desiccant. Suppose I use, so for 1 kg of air, suppose I use say 100 grams of the desiccant, maybe I will get humidity lesser than 0.0152 what I require. So I can always control how much amount of desiccant I use per kg of the incoming air.
Okay, sir.
Right. So all those things will come slowly in second year, third year. We are going to have separation processes where we talk about adsorption, and then adsorption is governed by its own equilibrium, like we talked about water, liquid water, and water vapor pressure. That's an equilibrium operation. Adsorption will have its own equilibrium. We call it as adsorption isotherm. And then depending on the adsorption isotherm, we may require less quantity, more quantity. Depending on how much water we want to remove, we will just choose the corresponding amount of adsorbent. We are not doing those calculations just now, but those will come automatically in your second year and third year. All right, shall we go forward now? Any other doubt? Anybody else? Anybody has any doubt? Shall we go to the next part?
Sir, also in the pressure part, if we are increasing the pressure, so
Right.
we'll have to heat it and depressurize it simultaneously, right? Because if we only depressurize it and then heat it,
Huh.
we'll lose more amount of water because the temperature would drop.
In the depressurization.
Yes, sir.
Yeah, okay. So obviously, when I heat also, when I compress also, the same thing applies for depressurization. The same thing applies for pressurization also. If I pressurize, automatically temperature is going to increase if I do
Yes,
it
sir.
adiabatically, right?
Yes.
So, but if I do it isothermally, which is more difficult to do, then obviously I will have to look at only the effect of pressure. Same way, when we are depressurizing, we can do it adiabatically, we can do it isothermally. Adiabatically is easier, but yes, temperature would fall and more water will condense out. But if I'm doing it isothermally, then I just have to worry about the effect of pressure.
Okay, sir.
So a lot more thermodynamics also is involved, which you will do in the next semester regarding how do I do compression, whether I can do it adiabatic, whether I can do it isothermal, which one requires more power, which one requires more energy, which one is better in terms of entropy. So we'll do all those things in this coming semester. But yeah, I mean, many things are there. That's why it's a 4-year course. So many different aspects we are going to learn. Okay, can we go ahead? You want a small break of 5 minutes, or can we go to the next part? Next part is, I hope everybody is mentally ready. We are going to talk about wet bulb temperature. Should we start? You need a break of 5 minutes. Refreshed? Are you tired from attending lectures the whole day?
So 5 minute break would do.
Yeah, so just a 5 minute break. So let's meet at after 5 minutes. All right. All right, shall we start? Are you fresh, ready to go? Anybody around?
Yes, sir.
Ah,
Yes,
Yes,
sir.
sir.
people are around. Very nice. Nice to hear that. That I'm not talking to a screen. All right. Uh, yes. Uh, so we are going to talk about two concepts. First concept, we are going to talk about heat transfer. So maybe 12th standard, 11th standard, or 10th standard. Did you do an experiment called as Newton's law of cooling?
Yes, sir.
Yes, sir.
Yes, sir.
Do you recall that? What you do is you take a beaker containing some hot water, right? And you measure the temperature of that hot water, and you note down the temperature as a function of time, and temperature falls exponentially as a function of time. Do you recall that?
Yes, sir.
So why does
Yes,
the
sir.
temperature fall? Why does the temperature fall?
Loss of heat to the surrounding.
Right, right. So if I take this beaker, I measure this temperature. Let's say initially the temperature was, let's say, 80 degrees centigrade. There is air outside. All around this beaker, there is air. Let's say this air is at a temperature of 30 degrees centigrade, right? So initially the rate of cooling is fast, meaning the rate of heat being transferred from the beaker to the air outside is very large. That's why the temperature falls very quickly, right? So if you plot, if I should draw a straight line, so if you plot temperature versus time, the rate of fall of temperature is initially very high, isn't it? And as after some time the rate of fall of temperature is less, after some time the rate of fall of temperature is less, after some time it is even less, after sometimes it is even less, isn't it? So rate of fall of temperature, meaning it is the same as rate of, whether I plot temperature or whether I plot rate of heat transfer from the beaker to air. Do you agree with that? Yes or no?
Sir, I think rate will be linear but
No,
decreasing.
whether it is linear or not linear, let us not worry about that just now, right? Let us not worry about whether it is linear or not linear just now. Do you agree that rate will be higher initially and rate will be lesser and lesser as this temperature falls?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Why is this cooling? Because this temperature is higher than this temperature. Heat is being transferred from 80 degrees centigrade to air which is at 30 degrees centigrade, and we are saying that air remains the same, air temperature remains the same, we are at 30 degrees centigrade. So if you say rate of heat transfer, this rate of heat transfer, you done some kind of Fourier's law, is proportional to temperature difference. So should we say 80 minus 30? After some time this 80 becomes 70, after sometimes it becomes 60, after sometimes it becomes 50, and so on. Do you agree with that?
Yes, sir.
Yes, sir. Yes, sir.
So now if I say that rate of heat transfer at, let's say this water is at a temperature T and this air is at a temperature some T air, the rate of heat transfer from this beaker to the air will be proportional to T minus T air, and this T will keep on falling. Do you agree with that?
Yes, sir.
Okay. Now suppose I take this beaker like this. Suppose it is 1 liter of water I take and I put it in a beaker, or I put it in a taller beaker, or I put it in the form of thousands of beaker, each one equal to 1 ml. I take one beaker of 1 liter capacity, or I take 1000 beakers, each of 1 ml. Which one, in which case do you think temperature will fall faster?
1000
So
meters.
second case.
In 1,000 acres.
Why is that? Why do you say 1000 beaker?
More surface area.
More
More
area.
surface
More
area.
area.
Very nice. More area. So this rate of heat transfer is also proportional to the area through which heat is being transferred. If it is one beaker, it is only the surface area of one beaker. If it is 1000 beaker, it is surface area of 1000 beakers, isn't it? So this rate of heat transfer is proportional to area through which heat is being transferred. Okay. And the temperature difference across which heat is being transferred. The temperature difference. The temperature difference. This, for a minute, we are going to call this as a driving force for heat transfer. Or if you don't want to call it as driving force just now, it's also okay. The rate of heat transfer is proportional to area. It is proportional to the temperature difference, which is responsible for heat being transferred from the beaker. Can we go forward? Is everybody okay with this?
Sir, more
Yes,
than
sir.
area, would it be the amount of the substance that is present?
Yeah, obviously, if I take 1 liter and if I take 5 liters, the surface area will also be different, right? Surface area per unit mass or per unit volume of the liquid. That is what is really important.
Yes, sir.
Okay, so right now let us just say area.
Sir,
Okay,
there should be a minus sign also, as it is a decreasing curve.
no, we have not yet. Wait. Uh, I'm just now saying it is only rate of heat transfer. I'm not yet talked about whether it is going out of this box or it is the same, na? Whether I talk about heat being transferred out of this box or heat being coming into the air. So if I say rate of heat transfer, if it is out of the beaker, it has a negative sign. If it is coming into air, it has a positive sign. Do you agree with that?
Yes, sir.
So right now I'm just saying rate of heat transfer, whether I'm talking about out of beaker or whether I'm talking about coming into air. They are same, right?
Yes, sir.
Do you agree?
Yes.
So right now I don't have to worry about sign. Do you agree with that?
Yes, sir.
All right. Rather than this proportionality sign, can I put an equal to sign? What will I have to do to put an equal to sign?
Constant proportionality.
Constant.
Some constant of proportionality. Let us call that constant of proportionality as H. Okay. This is constant of proportionality. All right. Is everybody happy so far? some jargon now. If you go and tell 12th standard students that this is what we learned in first year, how to convert proportionality into an equality, how to convert this proportionality into equality, they will say, what great things you are doing. We already know all these things. Why would you want to join ICT? Right? So we need to impress them so that they listen to you. Now that your people are in the second year, hopefully now once you go in the second year, once you go in the second year, these juniors, first year people should listen to you. So you must throw some jargon at them. They will say, how much knowledge you people have, and therefore they will be impressed by you. They will all listen to you. This jargon is this proportionality constant H. We give some name. We call it as heat transfer coefficient. Okay. Suddenly, now you can tell your second year friends, we also know about heat transfer coefficient. Don't brag to us. Now you have no reason to obey your second year friends. You also know as much about heat transfer as they know about heat transfer. Right? If you like, this rate of heat transfer, let us just call it as by some symbol Q. So if you want to rearrange this Q, you can rearrange as Q H A T minus T air. You can also say this Q is equal to T minus T air into A, and you can even say this is like 1 by H. This expression also we try to use many times. Does this look kind of familiar? Physics,
Yes, sir.
Yes, sir.
something something divided by something something. I is what? Current.
So voltage upon resistance.
Voltage upon resistance, right? So this is like the flux, or this is like the rate of heat transfer. So I will say Q by A. That's our flux. Going out of that box. T minus T air is like the voltage. We call this as driving force. Like the voltage is driving the current in a wire. The difference of temperature is what is driving the heat from the beaker to outside. And 1 by H is our resistance offered by this beaker air for transferring heat out of that beaker. So our electrical analogy or voltage analogy is current, that is our flux, is equal to voltage divided by the resistance, the driving force divided by resistance. Two important concepts, one or three important concepts. One is this rate of heat transfer is proportional to the driving force area. Proportionality constant we call as heat transfer coefficient. Heat transfer coefficient is same as 1 by resistance, or 1 by H is same as the resistance offered to heat transfer. So I will have to tell you something about this beaker, about this air, to actually find out about the rate of heat transfer. So just one thought process. If you take this hot beaker in a room, close all the windows, close the door, or you take the room, take this beaker, and you put 4 or 5 fans, which one do you think will cool faster?
The one with fans.
The one with fans.
Second one.
Correct. Now, so one with the fans, why is that? Area is the same, driving force is the same. Both had, let's say, initially 80 degrees centigrade. This also at 80 degrees centigrade. This air also is at 30 degrees centigrade. This air also is at 30 degrees centigrade. Driving force is the same, area is the same, identical beakers, but the rate of heat transfer is much, much faster here. Reason being, this constant of proportionality is higher in a place where fans are there than a place where fans are not there. So constant of proportionality or heat transfer coefficient depends on the situation. H depends on situation. Whether I am doing this experiment on Earth, whether I am doing this experiment on Mars, whether I am doing it on the Moon, whether I am doing it on Saturn, Jupiter, whatever is your favorite planet or favorite comet, wherever you want to do the experiment. It also depends on whether I have one fan, two fans, whether I have windows open, whether I have windows closed. So the rate of heat transfer will depend on the situation. Heat transfer coefficient depends on the situation. This is a very important concept. Whole of semester 5, there is a whole course on heat transfer. This whole course is based on this equation. Q is equal to HA into temperature difference. The whole course is based on this one equation. All right, we are going to look at many situations and how to calculate this H for different situations. If I have one fan, if it is on full speed, what is the value of H? If it is not running at full speed, what is the value of H? How do I calculate all that? All those things we are going to do in this course, but that whole concept is based on this one equation. Okay, that is one concept. All right, can we go forward? Anybody has any quick doubts? Anybody has any doubts? Shall we go forward?
Yes, sir.
Okay. This maybe we can just because you have raised the doubt whether the rate of heat transfer will be linear or not linear. We will again revisit this after some time if you want. Let's not get diverted from our objective today. Rate of heat transfer will not be linear, but that's okay. Second concept we are going to talk about is mass transfer. Okay. So the situation is analogous. Imagine a room and let's say I spray perfume in one corner of the room. I have fans going on, I have windows, I have doors, everything is there, they're open. Do you think if there is a person somewhere else in this room, do you think that person will smell this perfume?
Yes, sir.
If I spray enough of perfume, obviously.
Yes, sir.
Will he or she smell the perfume instantaneously or will it take some time?
So it will take some time.
It will take some time, right? And if I have the fan going around, or if I have windows open, or if I don't have them, I have stagnant air. I have air which is stagnant. Which case will I have faster transfer of perfume from the perfume can to the person sitting around?
Sir, in the case where the room has fans.
Correct. If it has stagnant air, it is only merely by a process of molecular diffusion. Do you agree with that?
Yes, sir.
Whereas if there are fans, then physically the air is going from one place to another place by the process of fan. So again, same thing we can talk about. What is the rate of transfer of perfume from one corner to the nose of the person? What can we say? Will it be proportional to concentration of perfume here minus concentration of perfume here? If I spray more, locally I have a high concentration of perfume. If I spray less quantity of perfume, locally I will have less concentration of perfume. If you like, suppose there are 100 molecules. If I look at this region and I have 100 molecules here, and I look at this region and there are 100 molecules here. Out of this 100, suppose 10 molecules are of perfume, and out of this 100, let's say one molecule is of perfume. Now there is random thermal motion, so molecules are going at random. So the rate of transfer of perfume out of this control volume of 100 molecules will be proportional to 10. The rate of transfer of perfume molecules out of this control volume of 100 molecules will be proportional to 1. So the net rate of transfer of perfume molecules from here to here would be proportional to 10 minus 1. If I have, instead of 110, suppose I have 100 molecules and 50 molecules of perfume. Isn't the driving force more?
So please repeat the last example again.
Okay. Let us say that I have this room. Let us say I have this room. I take a control volume here and I take a control volume here. Let's say this control volume contains 100 molecules. Out of that 100 molecules, 10 molecules are perfume and 90 molecules are air. And I take 100 molecules from this control volume. In this control volume, let's say one molecule is of perfume and 99 molecules of air. Are you able to visualize?
Yes, sir.
Now, the molecules that are in this room, they are in random thermal motion because the temperature is more than absolute zero, 30 degrees centigrade, 300 Kelvin. All right. So 100 molecules are, suppose out of this 100, suppose at in 1 second, suppose 20 molecules are going out. Per second. So some 20 molecules will also come in per second. Yes or no?
Yes, sir.
If this is my control volume, 20 molecules suppose come in, 20 molecules must go out per second. Otherwise my density will increase in this corner of the room. Is that possible? Density has to remain the same, right? Do you agree or do you disagree? Nobody is saying anything.
Yes, sir.
Yes. Yes, sir.
Now, suppose these 20 molecules are going here and 20 molecules are coming from here. These 20 molecules going out from here, how many air molecules, how many molecules of air will there be and how many perfume molecules will there be? Out of these 20, I will have 2 molecules of perfume and 18 molecules of air. Isn't it? Now, if I have 1 molecule of perfume here and 99 molecules of air here and 20 molecules come from here to here, how many perfume molecules will there be? It will be 1 divided by, it is 1 out of 100. So out of 20, how many will there be? It is 1 out of 100. So out of 20, how many will there be?
0.2.
So
Point,
point two.
0.2, right? So now let's not take 0.2 molecules. Let's say I have 5 molecules of perfume and 95 molecules of air. So now out of the 20 molecules that go from here to here, I will have 1 molecule of perfume and 19 molecules of air. Isn't it? Do you agree?
Yes, sir.
Yes, sir.
So now if this is the control volume, 2 molecules of perfume have come in, 1 molecule of perfume has gone out. Isn't it that there is a net transfer of 1 perfume molecule from here to here?
Yes, sir.
Yes, sir.
Yes, sir.
Is that okay? So the rate of transfer of perfume molecule is going to be proportional to concentration of perfume in control volume 1 minus concentration of perfume in control volume 2. Do you agree with that?
Yes, sir.
Same way, it will be proportional to the area of this control volume. Let's not worry about what this control volume is just now, but same way as heat transfer, it will be proportional to the area, and the proportionality constant what do you want to call this proportionality constant now?
Mass transfer coefficient.
Right, very smart. Who was that? Ansh. Mass transfer coefficient. And that mass transfer coefficient we are going to denote by a symbol small k. Again, so the driving force depends on the concentration, but the rate of transfer will depend on the area as well as mass transfer coefficient. If I have 1 fan, or if I have stagnant air, or if I have 25 fans all running at full speed, rate of mass transfer will be that much faster. Do you agree with that? So now several courses are going to be based on this mass transfer concept. Again, same way, this mass transfer per unit area, I can call it as flux of mass transfer. I'm going to denote by a symbol N. This would be proportional to K into the concentration driving force. If you want, you can write it as concentration driving force divided by 1 by K This is like the current, this is like the driving force, and this is resistance. So higher the mass transfer coefficient, lower would be the resistance. If I have 1 fan, 2 fans, 5 fans, 10 fans, mass transfer coefficient will be higher and higher and higher. Resistance will be lesser and lesser and lesser. Again, there are several courses that are based on this concept of mass transfer. Very important chemical engineering concept. Several separation processes are decided by this mass transfer coefficient. Okay, we'll talk more about it in the next semester. Semester 3, you have a course on momentum and mass transfer. We will talk about that, more about this in the 3rd semester. But right now, I just want you to understand, or I just want you to remember 2 things. Heat transfer and mass transfer, they are both very similar to each other. Rate of heat transfer or flux of heat transfer, Q, is proportional to heat transfer coefficient and the temperature driving force, and the rate of mass transfer is proportional to the concentration driving force, and the proportionality constant is mass transfer coefficient. Okay, everybody okay so far? Happy so far? Yes, no? Can we go forward?
Yes.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
All right. Now we are going to apply both these concepts to a situation, right? So imagine that there is a thermometer. Let's say it is in a air, ambient air. Let's say this ambient air is at a temperature of 30 degrees centigrade and it has a humidity of 0.02 kgs of water vapor per kg of dry air, or some kind of percent RH, maybe 70% RH, whatever, 60% RH, whatever, 50% RH, some value. So if I take a thermometer, I measure the temperature. What would be the temperature that I will measure? 30, right? Yes or no?
Yes.
Only one person is saying yes. If I take a thermometer and I measure the temperature, air is at 30 degrees centigrade, I will be reading mercury on that thermometer. That mercury will be up to 30 degrees centigrade. Do you agree? Do you disagree?
Yes, sir. I agree.
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now I take another thermometer. Okay. Obviously, that will also read at 30 degrees centigrade. But now I am going to do certain thing to this second thermometer. I am going to put a wet cloth around this bulb, right? I'm going to have a wet cloth around the bulb of the thermometer. And I'm going to keep it wet all the time. I'm going to ensure that there is liquid water in the cloth all the time. Okay. Now, suppose this is in one very big room, okay, or atmosphere, whichever, whatever you like. Is this air saturated or not saturated?
Not
It
saturated,
is
Not
and
not.
hence
saturated.
It is not saturated because it has only 70% RH. It has not. It doesn't have 100% RH. That means this air can accommodate more water vapor Do you see any source of water around?
The wet
Wet
cloth, and
cloth,
hence it would
right?
evaporate.
So some water from this wet cloth would evaporate. Do you agree with that? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Can we say there is rate of mass transfer of water in the form of vapors from wet cloth to the air? Do you agree?
Yes, sir.
Ah, if there is a transfer of water in the form of water vapor, that means some of the liquid water must vaporize. Yes or no?
Yes,
Yes,
sir.
sir. Yes.
If some of the water has to vaporize, would it not require heat? Would it not require energy?
Yes, sir. It will
Yes,
require
sir.
me.
Right. Now, who's going to supply energy?
Air.
No, air cannot supply energy because this also is at 30 degrees centigrade and this also is at 30 degrees centigrade.
So the
So,
mass potential would create.
right. So, if you look at the Boltzmann distribution, some of the more energetic molecules will escape. The kinetic energy of the remaining liquid water molecules will reduce, which means, in effect, in a layman's language, heat is taken out from this liquid water itself to supply for vaporization, latent heat of evaporation that is supplied by this liquid water itself, and therefore its temperature will fall. It will become 29, it will become 28, it will become 27. Now, if the temperature starts reducing, what this thermometer is actually measuring is not, it is not measuring the temperature of the air, it is measuring the temperature of the liquid wet cloth around it. It is measuring the temperature of that liquid water that is there in the cloth. Now that temperature starts falling, heat will be transferred from the air to the wet cloth, wet bulb, the cloth, wet cloth wrapped around the bulb of the thermometer. But rate of heat transfer is proportional to the temperature driving force, 30 minus 30, or 30 minus 29, or 30 minus 28, or 30 minus 27. If more amount of mass is being transferred, the temperature heat required is more than what can be transferred from the air, this temperature will keep on falling. It will fall to such an extent, it will fall to such an extent that the rate of heat transfer from the air to the thermometer bulb equals what is required for evaporation of water by way of mass transfer. And then the temperature will reach a steady state value. That temperature we call as the wet bulb temperature.
So can you please repeat the last statement, sir?
Yes, sir.
Let us do it quantitatively, then we will understand. I'm repeating the same thing. Only thing is, rather than talking in terms of words, I'm going to put in terms of equations. Is that okay?
Okay, sir.
What is the rate of mass transfer from the wet bulb to air? That would be mass transfer coefficient. multiplied by area multiplied by concentration of water vapor near the bulb minus concentration of water vapor in the air. Do you agree with that?
Yes, sir.
Okay. Now, if this is the rate of mass transfer, how much heat is required? The rate of heat to be supplied or rate of heat required for the evaporation purposes, meaning mass transfer of water, Ka C water vapor near bulb minus C water vapor in air. This is the amount, rate, kg per second if you like. How will I calculate the heat required? How much is the heat required? Heat is required corresponding to this much amount of water multiplied by latent heat of vaporization. Do you agree with that? This latent heat of vaporization, which water is evaporating? The water near the bulb is evaporating. It is the water which is at this temperature that is evaporating. So it is the latent heat of water at the bulb, wet bulb. Do you agree with that? Amount multiplied by latent heat. Yes or no? What is the rate of heat transfer? Do you agree or do you disagree? Hardik, you are asking me to repeat.
Yes, sir. Yes, sir. Yes, sir.
What is the rate of heat transfer from air to the wet bulb? It will be H multiplied by area multiplied by temperature of air minus temperature of the wet bulb. So when this rate of heat transfer equals the heat requirement for the evaporation of water for mass transfer, from mass transfer point of view, then this thermometer will reach a constant steady state temperature, which we will call as the wet bulb temperature, because the water will be at this temperature. Liquid water that is here will be at this temperature, wet bulb temperature. I have just repeated whatever I said in the words previously. So at steady state, heat transferred from air to the wet bulb would be equal to Ka C concentration of water vapor near bulb minus concentration of water vapor in air multiplied by lambda. Do you agree with this?
Yes, sir.
Yes, sir.
Yes, sir.
Thank you, sir.
Okay. Some of these concepts are little difficult to visualize, so you might want to, I will share the lecture as soon as possible. You might want to view this lecture over and over again. So rather than talking about concentration of the water vapor near the bulb, can I say that instead of concentration of water vapor near the bulb, can I simply say humidity near the wet bulb? And rather than talking about concentration of water vapor in the air, can I just say it is the humidity in the air? isn't it? Whether I talk in terms of concentration in terms of moles per meter cube, or I talk in terms of kgs per kg, it is one and the same thing. I will just have to have a different proportionality constant. So let's just call that as some k prime, because I am using a different set of unit of humidity. And then left hand side would be HA T air minus T wet bulb. So I'm going to rearrange this expression a little bit. Humidity near the wet bulb minus humidity in the air. This would be equal to, I'm just rearranging, H, this area will cancel out, divided by K lambda, temperature of the air minus temperature of the wet bulb. This is at steady state. It has reached the steady state temperature, which we call as wet bulb temperature. This lambda is of the latent heat required near that bulb. Lambda changes with temperature. Okay. This H by K is something special. Right now, this H by K is heat transfer coefficient divided by mass transfer coefficient, or K prime if you like, coefficient. This is some special number just now. That special number is a property. Right now you just have to believe me, but in the third semester we will prove this. This is just nothing but specific heat of air. Okay.
Sir, it's like taking the ratio of two extensive properties to get an intensive property.
Um, oh, H also is not a extensive property. H is also an intensive property uh, in some sense. In some sense, yes, you're right, but H is an intensive property because we have because already the surface area has been accounted for. So it is no longer dependent on the extent of the water. It is dependent on, so we have written Q by A, right? So flux we have written. So therefore H is no longer an extensive property. It is an intensive property in some sense. But yeah, I mean, so in a very loose sense, we'll talk about that perhaps next semester. But right now, let's not worry about whether it is extensive or intensive. This ratio just happens to be equal to specific heat of air. Only that much we need to worry about just now, or assume that this is some kind of law, but we will prove this in semester 3. So now this H wet bulb, humidity near the wet bulb minus humidity of the air, is now going to be specific heat, let's call that as Cp, divided by lambda at the wet bulb temperature, T minus T wet bulb, T of air minus the wet bulb temperature. Or basically I'm just talking about the air. So H is the humidity of the air and T is the temperature of the air. I can use this expression to calculate the humidity of the air. So if I take two thermometers, one which measures the temperature of the air, one which measures the wet bulb temperature. So I know these two values. I know the Cp of air. I know the latent heat for vaporization of water. I can calculate the humidity corresponding to the wet bulb near that wet bulb, and then I can use it to find the only unknown in this equation, the humidity of the air, in which I have these two thermometers, one with a wet bulb, one with a dry bulb, or one without the wet cloth. So, right, so I have to give you a value of Cp, I have to give you the value of lambda Wb, right? If I give you these two values, then I will know everything in this equation. T and T wet bulb I have measured, and then the humidity of the air we can calculate. That's how people measure the humidity of the air and calculate the relative humidity of the air. Whatever these weather people report, they measure the wet bulb temperature and they back calculate humidity and the relative humidity from there. Right? We will do some calculations so that we are clear about what we are doing. Right now, this air, this is Cp of air actually. It is specific heat of air, right? But this air does not contain only air as such. It has dry air part as well as it has water vapor part. So this Cp, if I take 1 kg of air, there is a Cp component for the dry air as well as there is a Cp component for the water vapor. Okay. So if you take 1 kg of that dry air, what you are actually going to get is Cp of dry air plus H times Cp of water vapor, because H is in terms of kilograms of water vapor per kg of dry air. So if you take 1 kg of dry air, what you get is actually 1 kg plus H kgs of water in the vapor form. So the amount of heat required per unit temperature rise is 1 multiplied by Cp of dry air plus H multiplied by Cp of water vapor. That is actually the specific heat of air because it is containing water vapor as well as dry air part of it. Humidity is in terms of kgs of water vapor per kg of dry. This lambda wet bulb, we will derive an expression for this lambda wet bulb after mid-sem. But right now I will just give you the value of lambda wet bulb. So if you take liquid water which is at 100 degrees centigrade, what is the value of lambda? Anybody knows? Latent heat of vaporization of water at 100 degrees centigrade.
4,200 joules per Kelvin.
Lambda has units of per Kelvin.
Sorry, sir. 4,200 joules per kg.
Okay, so it is not 4,200. It is 540 kilocalories per kg. Latent heat of vaporization of water. If you want latent heat lambda at any temperature, I'm just going to give you the formula, but we will get this formula after the mid-sem. It is 540 plus 0.55 into 100 minus T in degrees centigrade. So we are going to use this formula. Okay, don't worry where it comes from. We will get this formula after our mid-sem. It's very straightforward. Nothing complicated about it. I just now have to give you. I just have to give you now the values of Cp dry air and Cp of water vapor. If I give you these two values, now,
Sir,
yeah.
sorry, understand.
Go ahead, go ahead, go ahead.
So, shouldn't the Cp of dryer be multiplied by 1 minus H?
No, if I take 1 kg of the dry air, I get H kgs of water vapor free along with that, right? Whether I
Oh,
like it or not.
yes, sir.
So the net is Cp dry air plus H times Cp of water vapor.
Okay, sir.
The Cp of dry air is something like 0.24 kilocalories per kg Kelvin, and Cp of water vapor is about 0.45 kilocalories per kg Kelvin. So now our humidity relationship, wet bulb temperature relationship, is going to be like this. So Cp dry air plus H times Cp water vapor divided by lambda at the wet bulb condition, T minus T wet bulb. This expression we are going to use. Just one small point. So what we are going to do is we are going to measure temperature. We are going to measure the wet bulb temperature. Cp dry air I have told you, Cp water vapor I have told you, lambda water vapor I have told you. This H at the wet bulb condition, if you look at the wet bulb, this is your wet bulb, right? There is liquid water here, right? Liquid water is inside this wet bulb. The layer in the immediate vicinity of this liquid water, the layer of air in the immediate vicinity of the liquid water, what can we say about this layer in
Sir,
the immediate
Saturated.
vicinity?
the water vapor would be saturated at
Correct.
that
Air will
point.
be saturated with water vapor. That means if I take the wet bulb temperature, I calculate vapor pressure at the wet bulb temperature, then partial pressure of air in the immediate vicinity will be equal partial pressure of water vapor in the immediate vicinity. Water vapor in the immediate vicinity would be equal to vapor pressure at the wet bulb condition, and then humidity at the wet bulb condition near the wet bulb would be this partial pressure divided by 760 minus, or total pressure, I should not say 760, total pressure can be different from 760, minus partial pressure into 18 divided by 28.84. So knowing the wet bulb temperature, we can calculate this HWB. This can be calculated, right? HWB is nothing but vapor pressure at the wet bulb temperature minus, divided by 760, or total pressure, minus vapor pressure at the wet bulb into 18 divided by 28.84. So then the only unknown is the humidity, and we can then find out the humidity of the air. That's how we measure the humidity of the air. Okay, let's take an example. Suppose temperature is 30 degrees centigrade and the wet bulb temperature is 25 degrees centigrade. Can you find out the humidity of the air? Let's do this together. Okay, let's do this together. Temperature of the wet bulb is 25. So we will calculate vapor pressure at 25 degrees centigrade. Somebody calculate and tell me vapor pressure at 25 degrees centigrade.
23.5, sir.
23.6.
23.6.
Wow, you people are fast. 23.6 mmHg. Now, what is the humidity near the wet bulb? It will be 23.6 divided, let's say total pressure is 760. 760 minus 23.6 into 18 divided by 28.84. How much is that? Why does it take so long?
So 0.02.
Right, 0.02. Correct. Now let's put it in the formula. So our formula is HWB minus H, that is Cp of dry air, plus H times Cp of water vapor, divided by lambda at the wet bulb temperature, T minus wet bulb temperature. Okay, let's put in the values. H water at the wet bulb condition 0.02 minus H Cp of dry air 0.24 kilocalories per kg per Kelvin. H Cp of water vapor point, how it has become Wp, it is water vapor 0.45. Lambda at the wet bulb condition 540 plus 0.55 into 100 minus the wet bulb temperature, 100 minus 25, temperature 30 minus the wet bulb temperature 25. Right, everything we know. Only thing that we need to find out is H. Find out H from here. What takes so long?
So 0.0177.
0.0177 kgs of water vapor per kg of dry air. Okay, so what we have got is we have measured the temperature, we have measured the wet bulb temperature, we know the pressure, we know the values of Cp dry air, we know the value of Cp water vapor, we know the value of lambda, and we have calculated the humidity of the air. If this is the humidity of the air, can you calculate percent RH, and can you calculate the dew point temperature? Let's calculate. Air is at 30 degrees centigrade, wet bulb temperature 25 degrees centigrade, so humidity is 0.0177. I want you to find out percent RH, and I want you to find out the dew point temperature. Let's do this very quickly. Finding RH and finding dew point must be child's play now for you. It is so straightforward. What takes so long? Anybody doing? Not doing?
So 26.4.
26.
So what's the total pressure?
760. 760. 26.4 is what? RH or dew point temperature? Which one are you telling me?
RH. RH. RH.
RH is so small, 26.4. Are you sure?
Wait, sir. I'll check again.
So 88.6
What? RH or dew point?
RH.
Ah, better. Dew point?
So just a second calculating.
Sir, I am getting RH as 89.25%.
ठीक है यार, छोड़ दो. हाँ. Dew point?
So dew point 23.01 degrees.
Forget that. Zero, one, Baba. Who's going to measure temperature accurate to 100, 100th of a decimal? Anybody else?
Sir, I'm getting around 27 dew point.
So I'm getting 28.
No, 27, 28, both are wrong. I'll tell you the
So
reason why.
23 dew point.
Yeah, 23 is
It
okay.
should be lower than 25.
Yeah, it should be lower than the wet bulb temperature. Okay, let's just quickly do. So H is 0.0177. That means partial pressure divided by 760 minus partial pressure of water vapor in the air into 18 divided by 28.84 must be 0.0177. So then that means partial pressure, somebody calculate from this expression. Somebody calculate partial pressure of water vapor from here.
So 20.916.
Okay, so 20.92 mmHg. Now, what is percent RH? It is partial pressure divided by vapor pressure. Vapor pressure at what temperature? 30 or 25?
30.
So 30 because air is at 30.
Right. Right. That is the air can hold corresponding to its temperature. Its temperature is 30, right, into 100. So that's how you will get the percent RH. Now, dew point meaning what? If I cool to a temperature, such a temperature, when partial pressure now becomes equal to vapor pressure. So vapor pressure at what temperature is 20.92. And then use Antoine equation, you will get temperature. It will be around 23, something like that. Definitely less than 25. Snehal, have you got your mistake?
Yes, sir. I'm calculating. I think I made a mistake, but I understood it should be
Yeah,
less than 25.
sure. Okay. Okay, let me just give you a couple of more problems just for you to calculate. Okay. So let's take, say, temperature is 45 degrees centigrade. Dry bulb temperature is 45. Let's say wet bulb temperature is 35 degrees centigrade. Calculate percent RH, calculate dew point, calculate humidity. Okay, that's one problem. Second problem, suppose I say that the wet bulb temperature is 30 degrees centigrade. Let's say dew point is 20 degrees centigrade. Dew point is 20 degrees centigrade. Wet bulb temperature is 30 degrees centigrade. Can you find out the temperature of the air? Can you find out the percent RH? Can you find out the humidity? That is second problem. Third problem, let's say wet bulb temperature is let's say 20 degrees centigrade. Percent RH is suppose 50. Can we find out temperature? Can we find out the dew point temperature? Can we find out the humidity? Basically, out of these five, if I give you any two, you should be able to calculate the remaining three. The fourth, suppose temperature is 40 degrees centigrade. Dew point temperature is, let's say, 20 degrees centigrade. Can you calculate humidity? Can you calculate percent RH? And can you calculate the wet bulb temperature? Okay. So there are two ways in which we can measure the humidity of the air. One is to measure the dew point. Another is to measure the wet bulb temperature. Either you measure the temperature and the dew point, or you measure the temperature and the wet bulb temperature, and the humidity you can calculate. Okay. So let's do all these four problems, okay, as homework, and we'll stop here for the day. So please visit this lecture again, go through the lecture once again so that all these concepts are clear, and then solve these four problems that will sort of re-emphasize the concepts that we learned today. Okay, so we'll stop here for the day. I'll stop the recording.